Hi everyone. In the previous lecture, we began with our discussion on signal analysis, and we also looked at some important signals which one normally encounters in RF systems. We discussed about two important parameters of a signal, which is energy and power. We said energy and power are two important attributes for a signal, and we saw how to define them from their mathematical definitions. I also said we will look at the definitions of power in greater detail once we start discussing the design of an RF system. It's a very closely related definition to what we discussed in the previous lecture, but there are some more practical modifications to it. Now, we will continue with that discussion on signals. In this lecture, we will introduce a very important idea for signal analysis called the Fourier transform. In fact, the origins of Fourier transform began some 200 years ago in early 1800s when Fourier was working on solving differential equations, and he thought of that any periodic signal, as long as they obey certain conditions called Dirichlet conditions, can be expressed as a linear combination of sinusoids, and all these sinusoids are harmonically related. Okay, so all those frequencies are integral multiples of each other, of some fundamental frequency. Not only that, if you have a time domain signal and you represent it in a different form, called, which we will see that it's a Fourier transform, you transform it into a different form, and by the knowledge of that Fourier transform, we can greatly simplify or greatly have a better understanding of the signal, and also it will greatly help us in designing these signal processing and radio frequency systems. Now, this transformation of time to frequency, it's given by this very simple Fourier integral, where x of f is given by integral of x of t e power minus j 2 pi f t dt. In its simplest form, it's nothing but if you take a periodic signal, it can be represented as the sum of sinusoids. We extend the same definition to aperiodic signals. We generalize the definition and say that any signal can be represented by a continuum of sinusoids. So that continuum of sinusoids is the amplitude of those continuum of sinusoids is what the graph of the amplitude of those continuum of sinusoids is what we are going to call it as your Fourier transform. Now, this Fourier transform is a unique transform, which means every signal has a unique Fourier transform. So if you know your signal, then your Fourier transform is uniquely determined by that. And from the knowledge of Fourier transform, you can reconstruct your signal back. So that's this equation is called the synthesis equation. If you know what your Fourier transform is from the knowledge, because it's unique, you can reconstruct your signal back completely. So this equation is called the synthesis equation. The first equation is called the analysis equation. It gives you an understanding of your signal x of t, which normally you may not get by looking at it or staring at it in time domain. Okay, so Fourier transform is a unique transform. The next thing is this is something it's very useful when you interpret, especially we will later see when we are constructing this transmitted signals, what are the properties of this time domain signals and what kind of Fourier transforms can we expect from that. That will be very useful for us. If your signal x of t is real, we will very soon see that the Fourier transform will be conjugate symmetric around f equal to 0. So this is your y-axis in the Fourier domain. It will have conjugate symmetry. What do you mean by conjugate symmetry is that, let's say we take the Fourier transform at two different points. One is at f and one is at exact negative of the same frequency. They both will be complex conjugates of each other. Okay, so that's the property of conjugate symmetry. So x of f, you take at any frequency, you find its Fourier transform, and you find its value of its Fourier transform at a negative frequency. Okay, they both will be complex conjugates of each other. This is a property that Fourier transform for a real signal, it will obey this property. It's very simple to prove that. I'll spend a moment to prove it because it's a very useful property. If x of f is your Fourier, this is your Fourier integral x of t e power minus j 2 pi f t dt. Now I'll take complex conjugate of this. So I'll take conjugate of this whole integral. Okay, and then I'll bring this conjugate inside. Since x of t is real, it'll just be, so you have a complex number e power j theta. The conjugate of this will simply be e power minus j theta, right? It follows directly from the Euler's integrals. So you take a conjugate of this, you get e power minus j theta. So e power minus j becomes e power plus j 2 pi ft. So x star of f, x conjugate of f, is given by this integral. Now if you look at this equation, it resembles the Fourier integral, the analysis equation, except that there is no minus sign here. Now what I'm going to do is that I'm going to substitute f as minus f. If I substitute f as minus f, I'm going to get the exact Fourier integral. Okay, that will directly be equal to your Fourier transform. So what you get here is x star of minus of f, x conjugate of minus f is equal to x of f. So that's the complex conjugate property. It also tells you that you don't really need to know the negative frequencies. If you know only the positive frequencies, you can uniquely determine what the negative frequency is going to be, or what the magnitude of the negative the Fourier transform of the negative frequencies is going to be. Okay, if you just know the positive frequencies, that's sufficient. With that knowledge, you can easily construct the Fourier transform of the negative frequencies. Or this is also a test. Let's say you're given a Fourier transform, then immediately you can see that if your Fourier transform coefficients or your Fourier transform values exhibit complex symmetry, then you know that this is a Fourier transform of a real signal. Okay, it's a very useful property. It looks like a very simple property, but it's a very useful property. Especially when you're designing RF system, when you're designing a transmit or receive signals. Okay, so now we just said that they have conjugate symmetric property. So if I take magnitude on both the sides, what you get is x of f, the mod of that. Since if you take a complex number a, and the magnitude of a conjugate will also be same as the complex number before conjugating it. So therefore mod of x of f will be equal to mod of x conjugate of minus f, which will be equal to mod of x of minus f. So therefore you can see from here x of f, mod of x of f equals mod of x of minus f. So your magnitude function is an even symmetric function. Okay, so the magnitude of Fourier transform has to be even around f equal to 0. So it's a very useful property for a real signal. If you have a real signal, the magnitude of your Fourier transform will be even symmetric. It will be an even function in frequency. Okay, so it should exhibit a mirror symmetry around this axis. The second property, what about its phase? What will be the what kind of a function will the phase function be? So any complex number x of f, any complex number can be represented by its magnitude and phase. So the same way, since Fourier transform is a bunch of complex numbers, x of f can be represented as its magnitude and phase for different frequencies. Okay, for different frequencies, you will get different complex numbers. So x of f is mod of x of f e power j phi f. I'll apply this condition. This condition holds true for a real signal. For a real signal, x of f will be equal to x conjugate of minus f. So I'll take x conjugate of f. You'll get mod of x of f, it's a real number. Mod x of f is a scalar, it's a real number. Multiplied by e power, it's in place of plus j, you'll have minus j phi of f. Now I'll do x conjugate of minus f. This will be mod of x of minus f into e power j minus j phi of minus f. Now we just know from this definition, for a real signal, your Fourier transform is complex conjugate symmetric. So this value will be equal to x of f. Okay, so from this, equating the two, we already saw the magnitude function is even, magnitude of the Fourier transform is an even function in f. So it will cancel out and you will get the simple condition phi of f, the phase of this complex number or the Fourier transform, will be equal to minus of phi of minus f. So therefore, phase is an odd function. Magnitude is an even function, phase is an odd function. Okay, this is a very important property of Fourier transform. The next property is, what if x of t is real and even? I'm also adding another condition, x of t is real and even. So even, you'll include this condition, x of t should be equal to x of minus t. If x of t has a Fourier transform of x of f, you can easily show x of minus t will have a Fourier transform of x of minus f. Okay, it can be easily shown x of minus t will have a Fourier transform of, I mean, you just have to substitute t equal to minus t, and if you see your Fourier integral here, so I'll probably write it here. So you will have x of t, substitute t equal to minus t, you will get e power j omega t plus j omega t into dt. Sorry, this is x of omega. Okay, let me use f. So this will be plus j 2 pi f t dt. So this here is your Fourier transform. The only difference here is that instead of plus you have minus here. So if I put minus, so I can define a signal with a Fourier transform of x of minus f. Okay, just make a substitution x of minus t, you'll get this expression. You can readily show that. So if you're asked to find the Fourier transform of x of minus t, you can immediately show that will be equal to x of minus f. So compute the Fourier integral x of minus t e power minus j 2 pi f t dt. This is your Fourier integral. All you need to do is make a substitution x of t as minus t. You will end up getting an equation x of plus t e power plus j 2 pi f t dt. Okay, so of course there will be a negative sign here, that will be flipped once you flip the limits of integration. Okay, so and then you have this expression. If you compare this, this is simply x of minus f. Okay, here you have plus here, so you get x of minus f. So the Fourier transform of x of minus t is simply equal to x of minus f. So now if you see this equation directly, you get x of f. You take Fourier transform on either sides, you get x of f equals x of minus f. So what kind of a function is your Fourier transform? Is it complex now? If x of f equals x of minus f, is it complex? Remember, if you take the negative frequency, x of minus f should be equal to x star of f. They both should have complex conjugate symmetry. But you are getting this x of f equals x of minus f itself. So what kind of a function should x of f be? It's a real number or a complex number? Is it a real or a complex number? It has to be real, right? It has to be a real number. On top of that, not only it is real, but since x of f equals x of minus f, it is also real and even. So your Fourier transform x of f will also be real and even. So for a real and even signal, your Fourier transform will also be real and even. Now if you consider odd function, if you consider an odd function, you get x of t equals minus of x of minus t. So if you take Fourier transform on both the sides, you get x of f equals minus of x of minus f. Okay, remember you'll have to satisfy this condition. So I'll keep this in mind. X of minus f, the conjugate equals x of f. This follows from the conjugate symmetry property. You take complex conjugates on both the sides, I'll get x star of f, or x conjugate of f is simply equal to x of minus f. Okay, this follows directly from conjugate symmetry. So I can replace x of minus f here with, so x of f equals minus of x conjugate of f. Now you see this equation here. If x of f equals x conjugate of minus f, okay, sorry, minus of x conjugate of f, what kind of a number is that? It's, of course, x of f is a complex number. Is it real or imaginary? For example, if you have a plus jb, you take its conjugate, you get a minus jb. If you have a purely complex number, jb, then its conjugate will be minus of jb. It will be negative of the complex number. So here this equation tells us, if you take x of f and compute its complex conjugate, okay, you are getting minus of x of f. It means that x of f is purely imaginary. Okay, x of f is purely imaginary. Not only it's purely imaginary, you can also show that yeah, it's purely imaginary. I think that's a sufficient condition. And what can you say about magnitude of x of f? Will it be real, odd, or will it be even or odd? X of t is an odd signal, but it's a real signal. What can you say about magnitude of the Fourier transform x of f? Will it be even or odd? Odd, right? Because it's a real signal. Since x of t is real, that's a bigger condition. The moment x of t is real, x of f, the mod of the magnitude, has to be an even function. Whether it's even function or odd function, we don't care. Whether x of t is even or odd, it doesn't matter. Your mod of x of f will be uh, an even function. Okay, so that's one thing to remember. So that's it. These are some very important properties, some very basic properties. A few more. I'll discuss a few more properties as we go along this discussion. First, impulse signal. Impulse. It's a very trivial integral to calculate delta of t e power minus j 2 pi f t dt. Evaluate this integral, you will get 1 for all time, for all frequency. So the Fourier transform of an impulse is 1. Okay, so it means that all frequencies have equal energy here. Okay, such a spectrum is also called a white spectrum. A white noise is something, the color white can be obtained by mixing up all the colors with same proportions. So same way, this spectrum, which has equal magnitude for all frequencies, is referred to as a white spectrum. Now, we'll look at some important Fourier transforms that we have to remember. This is another, again, something that you can very easily prove yourself. I'll just look at some of the, yeah. Okay. If x of t has a Fourier transform of x of f, if you shift the function in time domain by say t seconds, then your Fourier transform is multiplied by e power minus j 2 pi f t into x of f. Okay, if you shift your signal in time domain, that's like a delay, so that's equivalent to multiplying by e power minus j 2 pi f t in frequency domain. Okay, so now if I have a signal delta of t with a Fourier transform of 1, if I try to find delta of t minus say t naught, I've shifted the impulse by t naught seconds, then the Fourier transform is going to be e power minus j 2 pi f t naught. Okay, so your Fourier transform is going to be this. What is the magnitude of this function? What is this magnitude of this function? E power minus, that's a complex number, exponential. So magnitude is 1. And the phase phi of f is simply minus of 2 pi f, minus of 2 pi t naught. Okay, 2 pi f t naught, sorry. Your phase is minus of 2 pi f t naught. I'll just define another important property in a few moments, but for our sake of for the sake of this discussion, since I'm talking about impulses, we will also look at, so here in time domain, if I have an impulse, in frequency domain, you can either expect a constant or a complex exponential. The magnitude of that should be constant, will be 1. The magnitude transform will always be a constant. There is one important property which I'll prove in a few moments. If you have a function x of t with a Fourier transform of x of f, if you consider the signal x of f, the Fourier transform of this signal will be x of minus t. So what is delta of minus t? It's an impulse at t equal to 0. So whether it's minus t, it will still be an impulse at t equal to 0. You can easily show this will also be equal to delta of t. Delta of minus t will be same as delta of t. In fact, this is something I'll leave it as an exercise. Delta of at can be written as 1 by mod a into delta of t. Okay, this is a very important, interesting property of an impulse function. This result can be proved very simply by using this fact that area under an impulse will always be 1. Using this condition, you can very easily show this result. Okay, so we'll use this property now. If I have a signal which is capital X of t, which is your, I've just replaced the Fourier transform variable f with t. The Fourier transform of that signal will be small x of minus f. So if delta of t has a Fourier transform of 1, the Fourier transform of a constant function, the Fourier transform of a constant function will be an impulse in frequency domain. So this is also called a DC function. A DC means it's a sinusoid of zero frequency. So all its energy will be present in at one frequency, and that will be f equal to 0. So delta of f. It's actually delta of minus f, but since delta of minus f is also equal to delta f, you get this equation. Now we will look at a complex exponential, e power j omega naught t. So this is a sinusoid, but a complex sinusoid. We'll use this simple property. The Laplace transform, the Fourier transform of delta of t minus t naught was e power j 2 pi f t naught. Now I have e power j omega t naught, omega naught t. So this is a time domain function now. F has been replaced. So accordingly, variables will also change it. So you will have 2 pi f naught into t. Okay. So then the Fourier transform will be an impulse. An impulse at a frequency of f minus f naught. Okay. So keep in mind, it's a time shifted signal. Here it is a frequency shifted in frequency domain. Your impulse will be shifted in frequency domain. So it's a sinusoid. A sinusoid means it's a single frequency signal. Okay, so all its energy should be lumped and be present only at a single frequency. So that's what this equation is, this Fourier transform is telling us. E power j 2 pi f naught is a sinusoid. It's a complex sinusoid, but still a sinusoid, which means it has energy at only one frequency. It has only one frequency. So that's why the Fourier transform is given by delta of f minus e, and that frequency is simply f naught. Okay, so if I shift in time domain, if you have an impulse, shifted impulse in time domain and frequency domain, you get a complex sinusoid. In time domain, if you have a complex sinusoid, you will get a shifted impulse in frequency domain. Now look at this signal, e power j 2 pi or e power j omega naught or j 2 pi f naught or 2 pi f naught t is a complex signal. Because it's a complex signal, what can you say about its Fourier transform? Is the Fourier transform, you don't have to worry about the conjugate symmetric conditions anymore. You plot your Fourier transform, it's a complex signal, and we just saw the Fourier transform, it's no longer an even function. Okay, the magnitude of the Fourier transform has to be an even function. But what you see here, the Fourier transform, of course, is a real number. It's a real number, but it's no longer even symmetric. The magnitude is no longer even symmetric. So this is a complex sinusoid. So that's what I was talking in the beginning. When you have complex signals, they will have asymmetric frequent Fourier transforms. By looking at the magnitude Fourier transform, you can quickly say if it's a complex or a real signal. The same way, if I take a complex sinusoid of e power minus j omega naught t, then the Fourier transform is, again, this is a result which can be easily shown. It will be delta of f plus f naught. Okay, here f naught is omega naught by 2 pi. F naught here is omega naught by 2 pi. Okay. Now we can, with the knowledge of these two complex sinusoids and their Fourier transforms, we can immediately construct the Fourier transforms of sinusoids. So a cos omega naught t, a cos omega naught t is a linear combination of two complex sinusoids, which is a by 2 e power j omega naught t plus a by 2 e power minus j omega naught t. Okay, so the Fourier transform, if I take the Fourier transform of this in time domain, it will be in frequency domain, this will be a by 2 into delta of f minus f naught plus a by 2 into delta of f plus f naught. So now you have two impulses, one at f naught, one at minus f naught, both of them with same amplitudes a by 2 and a by 2. Now cos omega naught t is a real signal. I constructed a real signal by adding two complex signals. E power j omega naught t is a complex signal, minus j omega naught t is a complex signal. I added the two signals and I got a real signal. Now, if you look at the real signal spectrum, you can see that it exhibits even symmetry, right? It is symmetric around f equal to 0. The magnitude function is an even function. The same way, you can also construct a sinusoid, a sine of omega naught t, using complex exponentials. And you can again show that the now sine omega naught t is an odd function. This here is an odd function. So your Fourier transform is purely imaginary. You can see here both the Fourier coefficients a by 2j minus a by 2j, they both are purely imaginary. So you get two, uh, two impulses. The first guy, f minus f naught, has a magnitude of a by 2j. This one here has a magnitude of minus a by 2j. So let's not worry about, yeah. So I can write it as minus of a by 2j. And if I take the magnitude, that will be the same. So you will get an impulse this way. That will be a by 2 and a by 2. So magnitude function is even symmetric. But you can see, because a sine omega naught is real and odd, the Fourier transform will be purely imaginary, but it will also obey this condition that it is even symmetric in magnitude, because the signal of interest is a real signal. Okay. Another important signal is the pulse signal. Again, this is a property I didn't mention before. If you have signals x1 of t, n signals x1, x2, and so on till xn, the Fourier transform of the sum of all these signals is the Fourier transform of the individual sum of the Fourier transforms of the individual signals. That goes without saying. It's a Fourier transform is a linear transformation, so it directly follows from that. The other most important signal is the pulse signal, the Fourier transform of a pulse signal. I'm not deriving these results, guys, because these are very simple results. What I expect you to know is have an intuitive understanding of them. So if you have a pulse signal of unit amplitude, let's assume the pulse signal amplitude is 1, and it lasts for t seconds. Let's assume the pulse is around origin, symmetric around origin. Then the Fourier transform is given by t sinc omega t by 2. So it will be t sinc pi ft. So if I expand this, I'll get t sinc t sine pi of t by pi of t. So you will get pi of t by pi of t. So this is the function you get. Okay, and I've plotted this function. The zeros of a sinc function will be at 1 by the time interval, 1 by the pulse width. So you'll get 1 by t, 2 by t, and so on. So if you plot its magnitude response, it's going to look something like this. So it will be sine waves, but their lobes will keep decaying. So this will be the main lobe, and the secondary, and the third, and so on. So these the powers of the amplitudes of these lobes will keep decreasing, okay, inversely with time. So that's a sinc function. Again, it's a real signal. So if you take its magnitude, it will be symmetric around t equal to 0. So you may have to remember this result, but it's an open book. So most of your tests are open book. So if you have a pulse, I'm going to write t of t, where t here represents the duration of the pulse. The Fourier transform is given by t sinc pi of t, where the definition of sinc x here is sin x by x. So it is t times sine pi of t by pi of t. Okay, it's a very useful result. Pulse, it will be a sinc. The other interesting problem is Gaussian function. What will be the Fourier transform of a Gaussian function? It can be shown, again, I'll just spend a minute to explain it. If you take a Gaussian function, t square by 2 sigma square, okay, I've just multiplied it with 1 by root of 2 pi sigma square, so that the area under this integral is 1. If you take a Gaussian function, the Fourier transform is also, interestingly, a Gaussian function. Now remember, no other function obeys this property. Only Gaussian function obeys this property. The Fourier transform is also a Gaussian function, but of course the variance will be different, but it is a Gaussian function. You can easily show why is that the case. You take x of t, this is a Gaussian function, differentiate it once. X dash of t, you differentiate it once, you will get minus 2t. Okay, so you will get minus 2t into the same function. You will get the same function multiplied by minus 2t by 2 sigma square or times x of t. So the derivative of this function x dot of t will be minus t of x of t. If you take Fourier transform on both the sides, again these things follow from Fourier transform properties. If you x of t has a Fourier transform of x of f, the derivative of x of t, the Fourier transform is given by j 2 pi f into x of f. Okay, you have to multiply your Fourier transform by j 2 pi f. Similarly, this result can be again easily shown if you differentiate your frequency domain, if you differentiate your signal in frequency domain, x of f. Okay, so let x of f be given by integral x of t e power minus j omega t dt or j 2 pi f t dt. And if you differentiate this d by df, you're differentiating with respect to f, only this term will undergo the differentiation. You have a j term here. What you will get here is integral minus j pi t minus j 2 pi t. So it will be minus j 2 pi t into x of t into e power minus j 2 pi f t dt. So this form of Fourier transform pair. So minus j 2 pi t into x of t and dx of by df will form a Fourier transform pair. So what you will get is minus j 2 pi f 2 pi t into x of t will have a Fourier transform of x dot here represents first derivative. So this is another important Fourier transform property. Using that, I can immediately show the Fourier transform also obeys a similar equation, differential equation. If you see, a Gaussian function obeys this differential equation. X dot of t, that first derivative, will be minus of t some constant times minus t upon into x of t. If you take Laplace transform, Fourier transform on both the sides. If I take Fourier transform on both the sides, I'm going to get plus j 2 pi f into x of f. This will be equal to minus t into x of t. You see here minus t into x of t will have a Fourier transform of x of x dash of f divided by j. See, I'll take this j into 2 pi to this side divided by j into 2 pi. So what you will end up getting, you take this term j to this side, you will end up getting is x dash of f equals j, there is a factor by sigma square here, I missed it out. So you will get 1 by sigma square. So x dash of f equals j square is minus 1. So you will get minus of 4 pi square sigma square x of f. Now look at this equation and this equation. We just said that a Gaussian function obeys this equation. And this term sigma square here will give me the variance of that Gaussian function. Now you see the Fourier transform of a Gaussian function obeys a very similar equation. The first derivative x dash of f, x dash of a Gaussian function here, what you have gotten here is the first derivative of this Gaussian function is 4 pi square sigma square x of f. It obeys this property. So therefore x of f will also be Gaussian. Okay, with the variance given by 1 by this term. Okay, there is a factor f. I think I've missed a factor f here. There is a factor f here. Sorry. Yeah. So it also obeys. You just replace the variable t. The only variables are t and f, but they also obey the same property. By this, I can argue the Fourier transform of a Gaussian will also be a Gaussian, but its variance will be 1 by the variance in time. It's frequency domain, right? So if you have variance in time, sigma has units of time, then in frequency domain it will be 1 by sigma, proportional to 1 by sigma. Not exactly say 1 by sigma, but proportional to that. So if you have a Gaussian function with a variance sigma in time domain, in frequency domain also you will get a Gaussian, but here the variance will be proportional to 1 by sigma square. In time domain, if it is sigma square, sorry, sigma square is variance, sigma is standard deviation. So your variance will be sigma square in time domain. In frequency domain, it will be proportional to 1 by sigma square. So if your function is narrow in time domain, it's going to spread in frequency domain. If your function is wide or widespread in time domain, or rather its variance is very high, in frequency domain you can expect it to be more and more narrower. Okay, so that's the Fourier transform of a Gaussian pulse. Only a Gaussian function obeys this property, where its Fourier transform is also a Gaussian function. Okay, and the variance of the Fourier transform of a Gaussian function will be inversely related to the variance in time domain. So narrower pulse, wider will be the pulse in frequency domain. So this is something I've discussed a few moments ago. If x of t has a Fourier transform of x of f, capital X of t will have a Fourier transform of x of minus f. That can be readily proven by starting with the synthesis equation, where x of t is given by integral x of f e power plus j 2 pi f t df. What we will do is we'll just substitute f equal to t on both the sides. So you get x of f equals capital X of t e power j plus j 2 pi f t into dt. Okay, just f is substituted, f and t are interchanged, it's just a variable, we interchange that. This looks like a Fourier integral. The only difference here is minus. So to bring minus here, I'm just going to substitute f equal to minus f. So I'll get x of minus f equals x of t integral x of t e power minus j 2 pi f t dt. It looks like a Fourier integral, and these two form a Fourier transform pair, x of minus f and capital X of t. So you have capital X of t, the Fourier transform of that will be x of minus f. So it's the principle of a property of duality. It's a very useful property because using this property, we can solve complex integrals. One such example is the sinc and a pulse function. If you take a pulse function of duration t seconds, I said that the Fourier transform will be a sinc function. Okay, the Fourier transform will be a sinc function. I have discussed Fourier transforms so far. X of f is given by integral x of t dt, x of t into e power minus j 2 pi f t dt. What is x of 0? If I'm trying to compute x of 0, what do I get? If you substitute f equal to 0, I get this integral. What is this value? That's the average value, or the area, it's the average value of the function x of t. Okay, it's the area under x of t. Okay, for an energy signal, we can also call it as an average. For a periodic signal, you'll have to do 1 by t. For energy signal, you can call it as the average. So that's the DC term. At f equal to 0 is a DC term. That value is simply given by this. So let's say I told you that, let's say using intuition, you know that the Fourier transform of a pulse is a sinc. So for a sinc, you need to know two things. What is the peak amplitude and what are the zero crossings? Zero crossings are periodic. So you'll have zeros at 1 by t, 2 by t, and so on. Okay, you will have zeros at all these frequencies. So where t here being the width of the function in time domain. So you'll have zeros at 1 by t, 2 by t, 3 by t, and so on. And the peak value here can be directly found by just finding the area under this pulse. So let A be the amplitude of this pulse. Then what will be the peak value? It will simply be A into t. So I can write A into t and times a sinc function, sinc of pi of t, because this pi of t I could write it because the zeros are at 1 by t. So it should be sinc of pi of t. And at, I'm multiplying it by at because sinc 0 is 1. So sinc 0 is 1. The way in which sinc function behaves, its value at 0, both numerator and denominator will tend to 0, and they will approach 0 in a very similar fashion. You have sin x by x. When x tends to 0, sin x is approximately x itself, so you will get sin x by x as 1. So your sinc of 0 will be 1, and the peak value can be determined by finding the area under this graph in time domain. So you know everything you need to know about the sinc. You know the zero crossings, you know the peak value. Zero crossings occur at 1 by t, where t is the time interval of this pulse. Using this, it's a very interesting property. We will use this property of duality. If a pulse signal has a Fourier transform of a sinc function, a sinc signal will have a Fourier transform of a pulse function. In time domain, if you have a sinc function, let's say the zero crossings occur at t because the units are in time now. So zero crossings are at t, 2t, and so on. In frequency domain, it's going to be a pulse. The signal is going to be a pulse. Remember, it's actually x of minus f. Okay, you'll have to take x of t, substitute minus f to it. But your pulse signal, if I'm going to assume that the origin is at the center, meaning if your pulse signal is an even function, it's symmetric around t equal to 0, then I can easily say x of minus f will also be equal to x of plus f. X of minus t will be equal to plus t. X of t equals x of minus t. If this condition is satisfied, I can directly write x of minus f as x of plus f itself. So x of t for a real and even signal, if x of f is your Fourier transform, then capital X of t will have a Fourier transform of small x of f. Okay, just have to replace time variable with frequency, you will get the same function. So for a sinc function, your Fourier transform is a pulse function. And the width of this pulse is given by 1 by the zero crossings, 1 by t. Right? You see here, first zero crossing, 1 by that will be t. So the same relationship holds here. So you now know the width of the pulse. The next thing you need to know is the amplitude of this pulse. Okay? The next thing you need to know is the amplitude of this pulse. Now, since it's a sinc function, let's assume you know the what is the condition that we can satisfy. If you integrate your Fourier transform, x of t is given by integral of x of f e power j 2 pi ft dt. What is x of 0? If you want to find its value at x of 0, that will simply be equal to x of f df, integral under the area under the Fourier transform x of f. So if you know x of 0, since it's a pulse function, let a be the amplitude be a dash, then a dash by t is the area under this graph. That should be equal to the value at origin, the value of t equal to 0. So from that, you can calculate, if you know this sinc function's amplitude, you can easily calculate what is the amplitude of the pulse function. And vice versa. If you know the pulse function's amplitude, you can calculate the sinc function's amplitude. Now, the interesting thing here is that we'll discuss a very important property. It's called the Parseval's theorem, or even a slightly more modified version. So let's say you have two signals x1 and x2. Then if you find its inner product, x1 into x2, the integral of x1 and x2, I'm assuming they both are real, this integral will be exactly equal to, in terms of its Fourier transforms, it will be x2 of f into x2 of minus f df. Okay, x2 of minus f and df. Now, if x1 and x2 are same, if they both are same signals, then you can write it as integral minus of plus infinity plus to minus infinity. I'll write mod of x of t the whole square. It doesn't make a difference. Equals integral of x1 of f, the mod of this the whole square df. Okay, I'm assuming real signals. If they're real signals, then this will become x1 of f. x1 of minus f will be equal to x star of f, x1 star of f, x1 conjugate of f. It follows from real signal properties. So you will get this. This theorem is called Parseval's theorem. The squared integral of the function in time domain will be exactly equal to the squared integral of its Fourier transform. Magnitude squared integral of its Fourier transform. This theorem is called the Parseval's theorem. Now, if you are supposed to find out integral, let's look at this function. I'll assume the amplitude in frequency domain, the amplitude is say 1. In frequency domain, the amplitude is 1. So the sinusoid, the peak value or the scaling factor or the peak value of a sinc is simply given by the area under this function, and that will be 1 into 1 by t. I'll call it f naught. Okay, f naught here is 1 by t. So that is f naught. So the sinc function looks like this. Now, if I ask you to calculate the energy in time domain, the energy in time domain is going to look like F naught square sinc square pi F naught t dt. So now you will have to evaluate a sinc square integral, and that's not very trivial. It's not very trivial to evaluate a sinc square integral. But using Parseval's theorem, we can quickly see that this squared integral is also equal to the squared integral of its Fourier transform, mod of x of f whole square df. And that if I square it and integrate it, because the amplitude is 1, so you will get integral, say, minus f naught by 2 to plus f naught by 2, 1 square df, which will be f naught. So now if you see, this integral is very easily solvable by using a Fourier transform property. That's one of the major advantages of Fourier transforms. I'm able to find the energy of a sinc function using this very simple condition. Okay. Now, if I want to define it in time domain, I said that f naught here is 1 by t. Since f naught is 1 by t, I have defined a sinc function of this type. 1 by t sinc pi f naught t. This is your sinc function in time domain. Its Fourier transform, its energy of this signal is f naught, which is equal to 1 by t. The energy of this signal is also equal to 1 by t. Okay, it's a very useful property. If f naught here is 1 by t, so I'll probably modify this a little bit and write it as pi t by t. So if you have a sinc function, sinc of pi t by t into 1 by t, its energy is 1 by t. So what will be the energy of sinc? I mean, let's assume sinc amplitude, peak amplitude is 1. So sinc pi t by t. What is the energy of this? The energy of this will be t. I mean, you can calculate that integral, sinc square dt. Okay. So the only difference here is, if we know this value of this f naught square integral is 1 by t. So if you remove the t, then you'll have to calculate that integral. You should get it as t. Okay, the Fourier transform of the sinc of pi t by t will be t into p 1 by t of f. It's a pulse function in time domain, in frequency domain, with an amplitude of t. So if you integrate this, you should get t square into f naught. So finally you will get t. F naught is 1 by t, so you will get t. It's a very tough integral to evaluate in time domain, but very trivial to do it in if you use this frequency domain approximations. Okay, so yeah, so I think I'll stop at this point. We'll continue with our discussion on Fourier transforms in the next lecture.